And I would like to acknowledge three companies here that have provided me with technology that was used in this for material in this presentation. Okay, our agenda is shown here. We'll just cover a broad overview of geomodeling. I'm going to discuss three core competencies, and so this talk is for both aspiring modelers, modelers, and people managing modeling, and that can include as well subsurface team members. So we'll discuss some of those concepts and the roles, and then in the second part of the talk, we're going to go into a little more technical detail, just highlight a few important issues. This is a huge subject, but we'll give you a flavor for some important areas and summarize. So geomodeling is an advanced platform to integrate and bridge the technical disciplines. And geomodeling has processes that can improve the effectiveness of subsurface teams. Those results can be used to improve decision making. That's if we're adopting these methods, and that requires buy-in from the team, the entire subsurface team, to be engaged, as well as support from the management. And that's just a picture of a pluri-Gaussian rule set. It's just transition statistics. So geomodeling, what is it? Well, it's a multidisciplinary subject, and we wear many hats when doing geomodeling. We have geology, geostatistics, geophysics, geomechanics. There's use of petrophysics and integration of reservoir engineering and engagement in the engineering and production processes. So it's a diverse subject, and so here we're wearing many hats, and yes, there's I have a beagle. And okay, so what does geomodeling do? Well, it's a technology-driven discipline. It uses digital information, that's spatial data, spatial information, which is combined with geological concepts. So we represent and honor reservoir heterogeneities, and reservoir heterogeneities are a combination of reservoir architecture described by the sequence of lithofacies, that is the rocks, and the variability of the rock properties within each given lithofacies. We use this information from the models for inputting the reservoir simulation for flow to understand reservoir performance, for planning purposes, to assess uncertainty, and make our overall reservoir plans. So these are just pad scale models showing facies. There's a nice mud plug channel, low porosity shown here in the mud plug, for example. So it helps us understand performance on a pad. Why do we do modeling at all? Well, there's a profit motive, of course, but in defining our projects, we're trying to enhance the net present value, today's value of the project as we plan it out into the future. We want to build efficiencies, and those efficiencies are in a variety of areas: timelines, production, carbon capture, emissions, improving emissions. And so the engaging in modeling improves the decision processes and the economics of projects. And there are barriers, of course, to new technologies. And so I just, this is tongue-in-cheek, but it's reality that some people have had poor results with modeling geostats, and so they're reluctant to use it. But one of the issues in our industry is that there are gaps in rules. We don't have industry rules around modeling. Sure, that's inside some companies that have their own internal processes, but there's no best practice guidelines in the public domain that are out there. The regulatory definitions are not used for geomodeling like they developed for 3D seismic and reservoir simulation. That's coming, but it's not there yet. And professional oversight is not well defined. Having review processes internally, externally, that's not matured. And finally, the ability to audit. There's no practices developed for the individual modelers to really record their steps and have repeatable processes and be able to review what they've done. So, you know, I'm a rule breaker. I like trying new things, but I encourage you to look into these issues. Geomodeling and geostatistics go hand in hand. There's ongoing challenges that exist to adapt workflows for our modeling needs to customize and etc. So one, we want to address new or unconventional problems. We want to apply actionable research results, actionable meaning that they're new methods, new ideas, and have them actually available to us in commercial software. We want to improve our workflow steps, and that does take sophistication. So this makes it an exciting field to be in. And here's just some teaser slides, colorful slides, some well pairs drilled and showing the quality of the rock, for example. There's been a real tremendous growth in the number of people practicing geomodeling in the last decade or two. There's a need for grounding in geostatistics, which is often missing in the training for the modelers. Mentors are in short supply. This is especially important in the smaller mid-sized companies. The large companies do have some mentorship. Training courses, they're definitely available for the software packages from the vendors. The packages are big, so the vendors have their hands full with that. So finding, there are a few available for fundamentals of geostatistics and very few on actual geomodeling practices that draw on specific topics, workflow elements. I mean, I do these courses. Then the universities are adapting the tools in their curricula. There are core competencies. It is a distinct, or should be treated as a distinct subsurface discipline. The three core competencies are, one, the grounding in geostatistics theory, and that's for the fundamental understanding of the engines behind multi-scale data integration. So that's behind the software. There's capability in software packages, and that's largely through the vendor training on algorithms, implementation, and application connectivity, that people gain those competencies. And finally, the practice, the thought processes, best practice, and tradecraft, the tools of the trade. And so if we grow all three competencies in our modeling community, that will grow the sophistication and openness. Modeling should be an open set of workflows. It should be a team goal to have the workflows adapted and transparent, and they should be adapted for specific play types. So organizationally, a strong team commitment will impact results and the ability to reframe subsurface practices for your teams when incorporating geomodeling competencies. This will mitigate bottlenecks and improve subsurface cycle time for teams. So there are values we should focus on. The ecosystem, and first encompasses the research groups, service companies, the government, regulators and researchers, and the overall industry, the E&P groups. And what we want is to cultivate the free flow of concepts, products, data interpretations from each discipline and each software. So our core modeling values, what they bring is to aim for sophistication. This leads to ability to adapt workflows. We want to grow communication across the disciplines through the toolkits and solutions. So that communication should be open, engaging, and spur new ideas. And we want to courageously reframe the subsurface practices using these competencies. And I'm saying we need to work at it to be open and grow this whole area. So geomodeling involves concepts to models, emphasizing this quite a bit. We start with our geologic concepts, sedimentologists, developing stratigraphy, what our stratigraphy is, and through understanding our engineering and analogs, this leads to our concept models. That drives how we interpret, how we classify facies, which are the important facies. We want to improve those facies through multivariate methods. We have seismic frameworks and attributes. We build our facies models, and we're after the statistical and physical behavior of our parameters and our reservoirs. So we're after parameters to get at the flow simulator. And another point is that reservoirs have heterogeneity, have variability. As we collect new data, the concept models take on complexity. And so over time, we go from a simple set of data and different working concepts to more certainty, more understanding of the local and known complexities. So modeling allows us to add complexity early in the early stages of our developments. And so geostatistical geomodeling helps to simulate that geologic variability early and capture the uncertainty with our scenarios. We have this concept model from a type outcrop, yet the subsurface has a lot of complexity to it. Here's this lateral accretion system with cross-cutting channels. So we want to allow for that uncertainty as we go through our modeling. This is a general diagram on the forecasting roadmap in a subsurface team. We have our concept models. We have some analogous reservoir information. The team is driven by that to make interpretations, do regional or area mapping. We're always looking at the geological and reservoir properties that relate to performance. And this main workflow here is that we build our models, simulate, and get those relationships to predict performance. So we want to use some of these relationships, if we can, to estimate performance. Let's discuss the statistical play type forecasting and mapping. So for an unconventional, tight unconventional reservoir, here's that flow that I just showed for the conventional of a reservoir model being built from our subsurface parameters. There's not a line of sight through this process to that production forecast. So we may take a different approach. But the issue is that the completions and production practices are altering the subsurface heterogeneities and the connectivity and in situ stress states. So in this approach, we could treat it as a statistical play. Take the actual production numbers that are known in the area, for example, IP60, 90, expected ultimate recovery, map those, and use the geologic parameters as a multivariate statistics, like we're using in the conventional flow, and infer the spatial distributions of the proxy models. So this opens up some newer methods, and yes, there are gaps in modeling, geomechanical parameters, but there's new multivariate methods, and working with proxies in the machine learning. This is a great opportunity here. From our forecasting workflows and these processes, another topic is uncertainty. So we have multi-realization models, we have scenario-based models, and we need to post-process, that is, just extract useful information. So we do want to check the model behavior and variability. We want to feed economic decision processes, decision trees, and economics. And again, we want to summarize and extract information. So here's just showing how we might have net pay thickness maps, and from low to high, and here's a P50. So these are useful, coming up with quantile maps and looking at the kind of spread of uncertainty that we might encounter. Another example, here's just a mapping example. We can get this right out of 3D models by summarizing in vertical columns over zones with our net. But here's showing an example of, say, the probability of higher than 9.5% porosity. Here's the quantile maps for simulated porosity, the mid-case quantile, low to high quantiles. And so these are just summary statistics. They're useful for planning purposes. Another way to use that uncertainty information is to integrate static and dynamic and predict performance without the full use of the cost, the CPU cost of simulating a reservoir. And this allows us to evaluate larger areas and make faster decisions, better early decisions. The example being you're having the relationship of various reservoir parameters and predicting some of our performance results here. And so we'll define some kind of drainage area. We come up with our multivariate statistics. We may have simulation or performance in local areas where we've done the heavy work. And then we take the dependent variables, the descriptive or independent descriptive factors. They're not always independent, but the descriptive factors for other drainage areas of interest, other potential pads, and predict performance. And these proxies can be response surfaces, either from functions, quadratics, and the uncertainty built with experimental design. Others might use rate equations and is physical proxies, so using state equations. So this can be calibrated with simulation, with production and field statistics, and these might also be commonly called type curves, but we're talking proxy models. So the reservoir modeling workflow if we lay it out in a sequence here, we define our project, our concepts, get our project set up, define structure and the framework, the set up grids and reservoir zones for modeling, scale the data, rescale that data, analyze at various steps, and then we get into the heterogeneity modeling. As stated, heterogeneity is that combination of the facies and the various parameters. So these are some of the common parameters. But we might be interested in also including some of our engineering and geomechanical parameters earlier or later in the process here. The multi-simulation post-processing is here. We do our analysis as earlier discussed. We may be looking at rescaling or ranking on some of these performance measures on the realizations to limit the number of models we simulate. Let's look at the subsurface evaluation workflow with a different graphic. We have the geomodel that we're going to build, and we're going to look at the G&G data interpretation, data gathering, and exploratory data analysis as a pre-processing to the modeling. We're going to treat the geomodel as the center of the process. So the entire G&G team would be focused on delivering the information for the structure model, strat model, attributes for trends, facies, logs, or electrofacies, and the various petrophysical measurements that are going to go into the process. But one of the key things is to get the team, if they're engaged, is to try to freeze inputs for the modeler, make it easier for the modeler to not have to do recycling before delivering early models. And then after the modeling, going through this workflow, there's the post-processing. So we're looking at extracting the information out of the models. And part of this is done by the modelers and some of it engaged with the rest of the team or engineering. But we might be looking at ranking based on, for example, connected net pay volumes or some other ranking measure. We may use the models for placing wells or simulation scenarios. And then, yes, we'll use them for performance prediction. And then a lot of this information goes into our decision processes. So field developments are data and engineering driven with complexities from recovery techniques and heterogeneous geology. So this is very much specific to the play type and development area you're looking at. We're always working with project timelines and planning for this. We have our subsurface projects and their cycle times for delivering results. We want to assimilate our new information, our delineation, exploration program information. We want to facilitate the decision-making processes and allow for improved technical work prior to decisions, and then provide improved decision options and risk assessment, risk management. So how do we do this? Well, by being engaged in this subsurface workflow and the geomodeling, we can plan for the data flow, cleaning, and feeding the models. And this allows for earlier delivery of data to the modeling, which allows more time for the simulation, forecasting, and economics. So proactive teamwork can help mitigate bottlenecks for modeling and the flow of information through teams, which improves the subsurface cycle time. Let's now switch gears and look at some subsurface workflow topics. So we could have a list here in text. We'll just touch on a few points, the frameworks, the heterogeneity modeling. We'll dig into the Facies modeling quite a bit and just kind of summarize petrophysics. And actually, we'll just touch on a couple of points beyond the model and conclude the talk. So recall this diagram, we just saw it, and so we're just going to refer to some of the pieces in here, okay? And then frameworks, we could have simple frameworks with stratigraphic layering like this in our wells, just our main sequence boundaries, or we could have quite structurally complex models where we need to understand the connectivity across faults and model according to that. The modeling workflows involve data from different areas, different different sampling of the subsurface. It's multi-scale data, that is, it has different volumes of measurement, support volumes. For example, core plugs, you can even go smaller, right? With some of the micro measurements. We have core, log scale, log sampling. We want to scale this kind of information into our grids. Seismic is often a larger scale and needs to be regridded or turned into probabilities. And then the geomodel and ultimately a flow model, which may be a larger or different scale, might be even smaller. So geostatistics is essential to addressing scaling issues in theory for averaging and non-averaging parameters. And there are other topics, I just list them here. We're not going to analyze all of them, but we have the inference of our input statistics. We want to make sure that we have fair statistics going into our processes. We have a number of model choices and testing to do, and then it impacts our uncertainty. And then checking the models, checking that we've honored the important statistics and the uncertainty model is fair. Okay, so then one of the key pieces of information to get the reservoir geometry and architecture is Facies logs, and their association with petrophysical curves. So this is just illustrating electrofacies. I have a talk in the geomodeling session as well on electrofacies. We'll go into more detail, but basically here's a visual interpretation of core and image data, and here's an electrofacies. So there are different kinds of logs, but the key is that we want facies that are consistent with the petrophysical information. So we have sharp high-res models, and that the multi-scale sampling can be done efficiently and properly. Okay, so well discretization, this is part of that scaling process. We have our Facies logs, our petrophysics, and we have a particular sample scale. We have a grid system set up. We want to sample the log, and we actually have a lot of choices on how we can go through this process, and the choices vary depending on the parameter. So the most common method for Facies is to use the majority Facies or the highest proportion in the grid block to assign. And so that this is an extreme image. Usually we're not jumping so high in scale that we have such detail inside. It's just for illustration purposes. And we have choices of averaging. Technically, we should just take the information in here as is and assign it to that new Facies. So we have a new Facies log with a blocked petrophysical log. But we could choose, for example, to only keep the petrophysical values associated with the highest proportion Facies. And so this is an example of the kind of choices. You can use random sampling, you can use midpoint, and we could go on. But other parameters like permeability, they're non-additive, so you don't necessarily use an arithmetic average, but you want to be careful not to to degrade it too much at this point. Water saturation, for example, would need pore volume weighting, or it should be weighted by porosity. It's only when you average it, it has to be averaged in the pore space, not the entire grid block. Another important topic is the vertical proportion curve. That's a very key statistical tool in the geomodeling process. We have our grid system, our stratigraphic correlation lines, and along those K layers or correlation lines, we can sum up the facies into the proportion, the percent of each facies. And if we have a variation vertically in the facies, that will be represented in the proportion. But what it does is it fixes the probabilities on each layer in the 3D model. So there's the structural framework, and we're working in the stratigraphic framework. We're setting up correlation lines. So then the choice of correlation lines and how we flatten the grids is illustrated here. Top down would be like an on-lapping sequence. So there's a lot of detail to how we choose this, but it should then give us proportion curves that reflect the geology. So this is just matching a proportion curve to an analog outcrop, and it's showing very much that we have these channel sands with some cycles, meter scale cycles, for example, and then a general fining upward pattern. And at the top, we have actually a coarsening upward in some shallow marine sediments. So this is very much a geological tool and a geostatistical constraint. And in moving it to 3D, we can use interpolation of local sets of wells, or we can use seismic. Here's from a good paper on the subject of using seismic. The volume support of a seismic measurement or seismic attributes, inversion parameters, is larger typically than the well log sampling or the volume of measurement of the well log. So the Facies log, for example, would have several samples for one sample of the seismic. So the appropriate or best practice use of seismic is not to predict an individual facies. That's a good exploration tool maybe, but for development, what we're after is the proportion or the probability of facies. So this sample here might give us a certain proportion of this yellow, the black and gray. We'd have a ratio defined. So that gives us 3D proportions, or this 3D ratio of facies, kind of like 3D net to gross mapping. Then we have conditional simulation of facies. Here we've got pixel and object methods are the main ones. Object methods are being used less these days than they used to, but and pixel, there's more options. And basically we're simulating one cell, one pixel in the model at a time. With pixel modeling objects, it's a group, so we're embedding shapes into the models. And so we're really after that architecture, the heterogeneity at the facies level, and this really does influence connectivity and flow in our models. and what's our producible pay volume. So we want to honor stacking patterns and reproduce transitions between facies. So here, objects are very appealing because in very sparse well cases, you can embed some connectivity concepts. And pixels, there's a lot more control now in getting these shapes. So here we have well facies, and common methods are truncated Gaussian, pluri-Gaussian, sequential indicator, and multi-point statistics. So pluri-Gaussian is really an extension of truncated Gaussian. We have here different directions of anisotropy shown, and it really allows us to have multiple processes or multiple anisotropy directions. This sets up different transition statistics that we can work with. We can actually honor the higher order set of statistics in the facies in our modeling, whereas something like SIS, it's very, it doesn't really do a good job of honoring our sedimentary stacking patterns. Multi-point statistics uses a training image, so it's our concept model. It can be from a variety of sources, aerial photos, old models that are reused, or object models can be set up, not conditioned to wells, and used to get the shapes. We condition to the hard data. This is binary. Seismic could be used either as in this example, as a binary of net and gross facies, or it could be used as a local proportion. This proportion might come from wells. We could have a version that comes from seismic, and we can combine them. So there's tools to combine these proportion trend maps in most of the software packages. We can also embed directional data to control shapes and affinities. So have thicker to thinner channels or distance from shoreline, and turn this image into that image in this conceptual model here. And training images can come from many sources. This is very commonly shown Strabel model. This is another kind of image. Here's a micro model, fractures, or an object model used as a training image. And here's a surface-based model. Surface-based modeling is becoming more prevalent as a toolkit for building training images. So there's a whole discussion to be had on this, but it is a way to honor facies transitions and higher order statistics, as they're called. So if we're working on improving our facies models, well, then we need for the full heterogeneity petrophysical model. So we want within each facies, we simulate properties in 3D. And those are typical parameters. We can extend that to mechanical parameters as well. So we have these. Then trends. Trends are very important. If we see trends, we should model them. Petrophysical trends can be apparent when you subset by your facies in the well logs. And so this is to get a good rock type model in the simulator. So trends do show up in saturation, porosity, V-shell, and even in permeability. Trends have physical explanations. They can be related to depositional environment effects, transition zones, compaction grain size, and capillarity. And certainly we want to honor those trends due to the facies and apply fluid physics concepts. So have that discussion with the team, engineering, petrophysicists, and model them. It'll improve the distribution of parameters in heterogeneity models. Okay, so remember this is a hierarchical workflow. We're modeling heterogeneity, Facies first, then porosity, and other parameters. A key, say for permeability, is to preserve heterogeneity, avoid over-smoothing these parameters like porosity and permeability. So if you can simulate them rather than using regression functions. And then static models do represent heterogeneities, so you want to define the important ones for your study, for your extraction and evaluation. And so this example shows the Facies model. There's an degraded intermediate zone, shows up in the porosity. Porosity is directly related to Facies. And we had these fluid effects. This is just the sand facies showing a strong two-zone capillary effect. So we have two transition zones. And that's reflected in this fluid distribution in the FISO plot that we use the trend and the wells, and we get a lateral variation and vertical. So in these zones, there's the transition and the effect of the facies here. Connectivity is yet another important factor to evaluate. So having an idea of how you're going to evaluate connectivity in your models is a group discussion. There's general concepts on connectivity from geology and the general idea that as net to gross increases, connectivity goes up rapidly. It's nonlinear. And that's very important for most of the model work. Although this kind of connectivity, just this direct net to gross system doesn't work perfectly for, say, thermal operations and unconventionals. But you want to come up with a plan here for your ranking, getting your connected net pay ranking and choosing realizations to take to the simulation. Whether you're a geomodeler, someone wanting to go into geomodeling, a subsurface team member engaging with modelers, or managing, there should be a motivation to grow these three competencies. Grounding in the geostatistical theory to better understand the underlying processes, and growth in understanding the software applications, and finally growing best practices. So you want to improve on workflow practices and document those. Let's build flexibility and sophistication through these three competencies, and this allows the teams to accelerate subsurface project cycle times. So in conclusion, we want to quantitatively simulate reservoir properties as is fit for understanding the physical processes used to extract the resource. Our understanding of reservoir heterogeneities changes over the life of the reservoir development. We should use the best possible geologic representation to feed the reservoir flow simulator. And let's account for all data and heterogeneities. The impacts on simulated flow behavior and forecasting are significant. So geomodeling continues to evolve. It's an evolving discipline. And today, geomodeling is essential to reservoir studies. And I'm teaching this course, just put a quick plug in here. Thank you very much. I'll also be delivering a short course, Introduction to Geomodeling Practice. We've set it as 5 half days for the online delivery. And we will repeat it. We need to confirm dates. So we'll repeat the course late March. And this information will be posted online shortly. The course is really to get across three core competencies, three core elements of geomodeling. We've got a summary of essential geostatistical theory, geomodeling thought processes. Will cover workflow elements and some key algorithms, and then as well include discussion of best practices in tradecraft. This is not taught by software vendors. Okay, so with that, let's go to questions on the talk on electrophases.